Hi, this is Mrs. Basin. Today we're going to talk about the line spectra and the Bohr model, which is section 6.3. So before we've talked about the wave nature of light, the particle nature of light, and when we talked about how to calculate the wavelength in the last section. And if you know the wavelength of light, then you can also calculate the energy of light in one photon or packet of energy. So we also talked about in the last section what a photon was, and a photon is a packet of energy or a packet of light. So the last set of notes, we talked about C equals lambda nu, which was the speed of light equals the frequency times the wavelength, or the wavelength times the frequency. Now we can look at E equals h nu, so the energy equals Planck's constant times the frequency. So another thing they were having a hard time explaining was that when you have this emission spectra, when you run electricity through a tube filled with gas, you see energy emitted by the atoms and the molecules. So what they noticed was the difference between when you looked at light, white light, that was passed through a diffraction grating or a prism, and you saw this continuous spectrum, which you see at the top there, versus when you ran electricity through something that only had an element in it, and it was like in the last slide you saw was neon light, that bright orange color. You see something a little bit different when you look at that through a prism or through a diffraction grating. So you only see certain lines. You see what's called a line spectrum versus a continuous spectrum. The other one they have up there, which you're familiar with from doing the activity in class, is the hydrogen spectrum. And notice you only see certain lines. You don't see that whole rainbow of colors. So Bohr adopted Planck's assumption, and he kind of tried to explain it in this way, which is kind of what that activity we did in class kind of proved. The electrons in an atom can only occupy certain orbits that correspond to certain energies. So if you can imagine on this drawing here, you have to kind of think of the nucleus as down here. And then this would be like the first energy level, this is the second energy level, the third energy level, and so on. So the electrons can only exist in these energy levels. And for them to get from one level to another level, they have to either release energy or absorb energy. He said that the electrons in these permitted orbits have specific allowed energies, and the energies are not radiated. So if they are in the orbit, they're not absorbing energy or releasing energy. And then the energy is only absorbed or emitted in a way as to move an electron from one allowed energy state to another. So the electron has to go from one level to another. It cannot exist in this space in between. One way to describe this is if you imagine climbing a ladder, you can only put your feet on the rungs of the ladder. So the rungs would be like the energy levels. You can't rest your foot in between two rungs of the ladder. So the electrons can't exist in between the energy levels. So since we know they're moving from one level to another, you can actually calculate the energy absorbed or emitted as that electron is either moving up or moving back down using the equation seen here. Now there's lots of variations of this equation. You have a couple different ones in your notes. The one that we used in class was not this particular one exactly, but you see the one here, but you have the one in your notes that we used in class. So you can use any of these as long as you put the variables in the right place. So what this one does is it gives us the change in energy associated with an electron going from one level to another. RH is the Heisenberg constant, so that's given there. And then the N's stand for the energy levels, and N sub I is the initial energy level, N sub F is the final energy level. And when you do this, you're either going to get a positive or negative number, and that positive or negative number is going to correspond to whether or not the electron is emitting that energy or the electron is absorbing that energy. So let's look at an example here. Now I'm going to use a different equation since we used that first equation a lot when we did all those calculations in class. I'm going to use another one just so you can see a different way to do this. This one says calculate the wavelength of light that corresponds to the transition of an electron from n equals 4 to n equals 2. And then we want to know is the light absorbed or emitted. So I'm going to use the second equation in your notes, which is frequency equals the Heisenberg constant over Planck's constant times 1 over the initial energy level squared minus 1 over the final energy level squared. Okay, so that's going to give us the frequency. Then we're going to have to do a second equation to get to the wavelength. So what this looks like is this is my 2.18 times 10 to the negative 18th joules over Planck's constant, 6.626 times 10 to the negative 34 joules seconds, and then multiply that by 1 over 16, because this was my initial, minus 1 over 4, because that's my final. So then when I calculate that, I get a negative 6.17 times 10 to the 14 hertz, because this is a frequency. Okay, and that negative number means that light was emitted. Light was given off. Okay, after I have a frequency, then I can use my C equals lambda nu to solve for wavelength. So my wavelength ends up being 4.86 times 10 to the negative 7 meters. Or if you wanted to put it into nanometers, you could, which is about 486 nanometers. And you probably know now from doing the activity, you could probably estimate where that, or what color that line is, what color you would see for this particular transition. The last thing in this section is to look at what's called the Heisenberg uncertainty principle. So what Heisenberg said, as they started adding and looking at what's called quantum mechanics, they realized you can't know the exact position, direction, or motion and speed of subatomic particles simultaneously. So basically what that means is the more you know about one of those pieces of information, the less you know about another. And this has to do with that dual wave particle nature of light. So he said that specifically, the more precisely the momentum of the particle is known, the less precisely its position is known. So kind of the takeaway here is you don't know exactly where the electron is. You have maybe a very good idea of where the electron probably is, but you can't know exactly where it is, because the more you know about one piece of this, the less you know about the other.